This is chapter 9.5, exercises 31 through 40. This section of the book has to do with series. And we're going to look over the odd numbered problems, 31, 33, 35, 37, and 39. And exercises 31 through 34 express the rational number as a fraction of integers. And to tell if we have a rational number, what we look for is repeating decimals. And this is a example of repeating decimal, this 1-4. Some common repeating decimals that you're familiar with, I hope, are this 0.333 and so on, right? That's going to be 1/3, or 0.111 and so on, approximates 1/9. Well, here I'm going to enter these in a calculator. So this is kind of a calculator exercise, really. And I have my TI Inspire CX calculator, and I've pre-entered this number for problem 31. And I go to menu and 2, which is number, and then option 2 again, which is approximate to fraction, and we press enter. And we get this fraction here, 5, let's see, is it 51,010,000 over 7,142,843. And so I'm going to go write this down, and I'm going to write down approximately equal to, and because that's approximately what it is rounded. And so we have 51 million, and that's going to be 10,000. Let me see if that's right. Yeah, that's right. Over, we have 7,142,843. Now, I also did this problem on a TI-84 calculator, and as you soon will see, we're going to get a different answer. And here's a TI-84 keypad. That's a TI-84 Silver Edition calculator. And here we have, now you notice that we had in the original problem 4 repeating sets of 0.14. Well, here we have a 5th, because when I tried 4, I didn't get anything as far as converting to a fraction. And so after you enter the number, the first thing to do is to press the math key. And so here's the math key. We press the math key, and this is what we get after pressing the math key. And the next thing we're going to do is press the 1 key. There's the 1 circled in red. We press enter, and this is what we get. And it says convert to fraction, and the 7 point is over to the left. We don't see that. And then the last thing we press is enter, which I've circled in red. Press enter, and we get this fraction, 707 over 99. And so going back to our sheet here, we can put or 707 over 99. So that's another possibility, but this time using a TI-84 calculator. Next odd number problem we're going to look at is 33. We have negative 17.268,268,268. So 268 is our repeater here. And going to the TI Inspire CX calculator, we're going to put negative 17.268,268,268. Same process as before. We press the menu key, 2 for number, 2 for approximate fraction, press enter. In this case, we get negative, let's see, that's going to be negative 431,771 over 3,771,000. 731,224. So we go back here, and I'm going to put approximately equal to, I'm going to put negative 644, 644, 31777, and so that's going to be that with the commas over 3731224. And it so happens that I worked this same problem out, but this time using a TI 84 Silver Edition, put SE for Silver Edition, and that answer is going to be very close, but is negative 17,251 over 999. So the answers you get depend a lot of times on which type of calculator you use, but in each case they're going to be very, very close to the original rational number that's written in decimal form. Next odd number problem, savings account. Practical real-world use of series. And we have the table below shows a December balance and a fixed rate compound savings account each year from 1996 to the year 2000. So 5 years. 1, 2, 3, 4. Well, there'll be a span of 4 years. But the balances form a geometric sequence. What is R? Well, you might recall that R is equal to A sub n divided by its prior term. So if we take A sub n divided by A sub n minus 1, in this case we can take any two successive terms. We'll take the two first ones we had here, which are 22,000. We'll say A sub n is 22,000, and A sub n minus 1 is 20,000. Now, that should be pretty easy to figure out what it is, but just in case it isn't, we go to calculator, we press control, and the division 22,000 over 20,000. We get 11 tenths, and we go to, that's 1.1. 11 tenths is 1.1. So we go back here, and we'll say R is equal to 1.1. And we could have taken any two succeeding terms. We just picked the first two. Write a formula for the balance of the account in years after December 1996. Well, for this, I'm going to write this kind of in function form. We'll say P sub n, which is amount sub n. Let me put A sub n for amount. A sub n, which is the amount as a function of the input value of n, equals our initial term, which is 20,000, times we have R, which is 1.1, to the power of n. So saying, sometimes you'll see this written as the power of n minus 1. Well, in this case, we have for each year, so 1 year, 2 year, 3 years, 4 year span, so n will have to be 4, so that'll be the account balance there, and that's the formula. And so we could see what that account balance is going to be. We could just put in 2, 3, 4, 5, let's see, 5, 1, it's the power of 1, that'd be right. So if we put this formula to the power of 5, 20,000 times 1.1 to the power of 5, we should get what the answer says, right? We should get, let's try that, 20,000 times 1.1 to the power of 5, we get 49,000. So that's not right. Let's try to the power of 4. 2,000, 20,000 times 1.1 to the power of 4. We're going to get 29,282, which is what they give in the table for the answer. So n in this case would be 4. So let's go back here. There we go. Now find the sum of the December balances from 1996 to 2006 inclusive. And for that, we can use a finite series. And that finite series is exactly this. Let me write this down. We have, if we want from k equals 1 to n of a sub k, we get a sub 1 times 1 minus r to the power of n, and that's going to be over 1 minus r. So in this case, what we have is $20,000 times 1 minus 1.1 to the power of 11 over 1 minus 1.1. And going in our calculator, let's do that. 20,000 times 1 minus 1.1 to the power of 11 over 1 minus 1.1. And for that, we get $370,623. And that's going to be in dollars. Okay, so these will be our answers for parts B and C. If you look at problem 36, somewhat similar, but problem 36 is instead using an arithmetic sequence. So you're looking for D instead of R, common difference. And then there's the formula for the common difference, the finite series. Anyway, that's going to be n over 2 times 20, a sub 1 plus a sub n. So kind of the average. Okay, next on the problem 37. Mr. O'Hara deposits $120 at the end of each month into an account that pays 7% annual interest compounded monthly. After 10 years, the balance in the account in dollars is, and we're given a formula, and this is a sequential formula, and you're given the first two terms and the very last term. This is a geometric series. What is the first term? What is the common ratio R? So the first term is this thing right here. So first term is equal to 120. In this case, 120 meaning $120. And then let's see, what is the common ratio R? Well, common ratio R is going to be this thing right here. This is R. So R is equal to 1 plus 0.07 over 12. So that's the value of R. And that's the common ratio right there. That's our answer for part A. 2 parts. Okay, next. Part B. Use the formula for the sum of finite geometric sequence to find the balance. Well, for a finite sequence, I'm going to write this out in blue, of from k equals 1 to n of a sub k, which is a summation, is equal to a sub 1 over 1 minus r to the power of n over 1 minus r. And for that, what we have is 120 times, which is a sub 1. In this case, they call it a sub 0, right? That's a sub 1. We have 1 minus r, which is 1 plus, I'll say 0.07. Minus 1 plus, I'll put 0.07 this time, over 12 to the power of 120. And I'm going to second parentheses here. And all that over 1 minus r. So 1 minus 1 plus 0.07 over 12. And what is that going to be? Well, let's go to our calculator. And let's go to control division. We have 20,000, no, 120, excuse me. 120 times 1 minus, open parentheses, 1 plus 0.07 over 12, and that raised to the power of 120, and we take that over 1 minus r, so 1 minus, same thing we have above here, 1 plus, okay, division bar, 0.07 over 12, and we get this value, which is $20,770.18. And problem number 38 is very similar, just a different a sub 1, different interest rate, otherwise the same type of problem. Problem 39, group activity, follow the bouncing ball. When super balls sprang upon the scene in the 1960s, kids across the United States were amazed these hardware balls could bounce to 90% of the height from which they were dropped. I actually think they bounce a little higher. If a super ball is dropped from a height of 2 meters, how far does it travel until it stops bouncing? Gives a hint. The ball goes down the first bounce, then up and down thereafter. And so for that, I want to just show you, I went and got a quick Wikipedia article with the super ball. Shows the inventor, Norman Stingley, and how it was manufactured by the Wham-O Corporation. It was a fad, and it was a very it's quite an invention to be able to build something as resilient that would maintain so much of its energy and bounce so high. Okay, back to the problem here. how far does it travel until it stops? Well, hint, the ball goes down to the first bounce, then up and down thereafter. What we're going to use is the infinite series. And that infinite series goes like this. You have from n equals 1 to infinity this time of a sub n, it's equal the first term a sub 1 over 1 minus r. That's all we need. Now in this case, your ball is going down, so what you have is 2 meters before the first ball is dropped. So 2 meters plus, well, a sub 1 is going to be 2 meters, and we're looking at 90% of the height, so times 0.9, but taking into account that the ball is being dropped, let's say, from 2 meters, okay, that's 2 meters, and it bounces up again to 90% of that height, so 1.8 meters, and then down again, bounces up to 90% of that height, and so on, infinitely, right? The ball will never stop bouncing. But how far does that ball get? Well, it's going to look like it stops bouncing because after time, the bounce will be so small, it'll have gone its full amount of distance, starting with the 2 meter drop. And another thing we're doing is, since we're going down, since it's bouncing, the ball goes up and then down again. So we have 2 times 2 times 0.9. That's going to be our a sub 1. And over 1 minus r, well, r is going to be 0.9 for 90%. And so now I think we should have everything we need to put in our calculator and get this right. So we go to our calculator and we press in 2 plus, we get our division here. We have 2 times 2 times 0.9 over 1 minus 0.9. And here we get 38 meters total. So it's a 2 meter drop, then 36 extra meters vertically. So we go back here and we'll put in 38 meters total. And that's the amount the ball travels vertically after being dropped. 2 meters to the ground, and then that bounce. And again, our a sub 1 is going to be 2 meters times 0.9. So this is kind of a typical series problem. You see problems like this. Problem 40 we're not going to do, but it has to do with what happens when the ball bounces higher. Okay. I think we're going to get a divergent series in that case. Anyway, good luck on your even numbered problems for this set, and thanks for viewing.